So we're about to kind of round up our discussion or round off our discussion of concurrency, and then we'll move on to parallelism next time. So let's talk about the history of concurrency support in Java, give you a little bit of a history lesson. If you have known Java and used Java for a long time, you may be aware of some of this stuff. If you're fairly into it, this may be something that you have never heard of before, but it's kind of interesting to see how things evolved over time. So back in the day, back in the mid-90s, there was a programming language released by Sun Microsystems called Java. It was based on something called Oak, which was preceded a few years. And the very first version that hit the streets back in 95, Java 1.0, supported Java threads and so-called built-in monitor object. So what are these things? Well, before we get into the details of what they were, let's also just be honest about what they did. This was back a while back, almost 30 years ago. It's hard to believe. The focus there was on very basic multi-threading and synchronization primitives, the kinds of things that you could expect to find or implement on almost every operating system around that time. And there was a little bit of churn at the beginning because not all operating systems supported multiple threads, but they had a fake way of doing it using something called green threads, which ironically are not too dissimilar to our modern notion of Java virtual threads, but Java virtual threads are way cooler. So let's take a look at an example. Here's an example of using threads. This is something you can get from my website. It's a simple blocking queue example, which is better than the buggy queue we looked at before. And simple blocking queue is going to create this bounded queue that's capable of being blocked. You can have things wait to remove items when there's nothing in there and wait to insert items if the queue is full. And so this allows a bounded buffer to be implemented, very common concurrency abstraction that's talked about ad nauseum in almost every textbook on concurrency. So we make one of these things, and then we go ahead and we create two threads. And notice we stick them into a Java array for various reasons. And thread 1 is going to be the producer. It's going to have the queue, and it's going to write items to the queue. And thread 2 will be the consumer. It will read items from the queue. They're sharing that bounded buffer. And once we've created that array, then we iterate through all the threads in the array, and we start each one. There's only 2, but we start them that way. And I mostly did this so that everything would fit on one slide. And once those are started, they're going to go off, and they're going to do producing and consuming between that simple blocking bounded queue. And then the main thread, the thread that started the other 2 threads, the thread that's the parent, if you will then join, waiting for the threads to finish. So join is essentially a simple form of barrier synchronizer that waits for the other 2 threads to complete. So that's sort of threads 101 or threads 1.0. There was also support for so-called built-in monitor objects, which supported mutual exclusion and coordination using some methods and or keywords that were added to Java as well. So here's an example of the take method. The idea of take is to remove an item from the queue if there's an item available, otherwise block. And the way this works is it used the synchronized keyword. Synchronized can be used both at the method level and also at a statement level. So we have a synchronized statement which says wait and only let one thread in at a time, so we can have a critical section in the synchronized block. And then while the queue is empty, we don't just spin neurotically saying, is it there, is it there, is it there? That would be very wasteful. Instead, we put ourselves to sleep by calling wait. Wait is a built-in primitive that comes from Java object, and it basically puts the thread to sleep until it's notified by someone else. And when it's notified by another thread, it'll wake up and then check to see if the list is still empty or not. This is called a guarded condition. It's the guarded suspension pattern. And if it turns out that it is indeed not empty, then we break out of the loop, and then we tell anybody else who's waiting that we've just removed something or about to remove something from the queue. And with the synchronized intrinsic lock still held, we then go ahead and remove the first item from the queue and return it, and then on the way out, the synchronized statement will release the lock. So some other thread can come along and be part of that critical section. So that's just kind of classic. This is actually the monitor object pattern, which is something I wrote about many years ago. This is also using the guarded suspension pattern, very common way of doing things in concurrent programs. These mechanisms that were in Java 1 were very efficient, but they were low level and limited in what they could do. As a consequence, there's all kinds of accidental complexities, which can arise from limitations with software technique, software tools, software methods. These are things that are not inherent in writing code or writing concurrent code. It's because we're using tools that are very limited. So you can learn more about some of the problems with these mechanisms. But in a nutshell, they were too low level for their own good, even though they were very efficient. Therefore, Java 5 came along in 2004 and added a slew of other stuff. The executor framework, a whole slew of other synchronizers, things like reentrant lock and reentrant read-write lock, and semaphore, blocking queues, array blocking queue, link blocking queue, atomics, atomic integer, atomic boolean, concurrent collections, concurrent hash map. All those things became available in Java 5. And the focus there was on coarse-grained task parallelism, coarse-grained task parallelism. And basically, the idea here is that tasks, which are an abstraction, can run concurrently within a pool of threads. And the assumption in the 2004 timeframe was that there weren't really very many processor cores. There were typically 2 or 4. That was about the extent of what we had in those days. So you had some concurrency, but it wasn't an embarrassment of riches, and it wasn't an abundance of concurrency. And we will not talk about this in much detail, but this is one of the cool abstractions that was from that time called the executor completion service, where you could submit tasks that would run in a thread, in a pool of threads, and then when the computation was done, the results would be put back on something called a completion queue, and then the caller could take the items as they finished. So you had this kind of cool little pipeline mechanism going on. There's a really neat example. If you ever take my CS254 course, we're going to do a lot of stuff with this, where it's called a Palantiri Manager. And what we're going to do is we're going to create a fixed size pool of threads to coordinate, and then we're going to coordinate starting and stopping tasks that acquire and release the resources that are shared between the threads. And the example for all you Lord of the Rings fans out there is we have some Palantiri, which are the mystical seeing stones you can use to communicate within Middle-earth and other places. And then we're going to have a number of beings from Middle-earth, and they're going to take turns gazing into the Palantiri that they have access to themselves. And it's a great example of essentially a resource management problem in a concurrent environment. So to do this, we're going to allocate a fixed pool of threads with one thread per being. And then we're going to go ahead and we're going to create a couple of synchronizers, a cyclic barrier, which is going to have all the threads, all the beings, wait to start running when they're all ready to go. So that's what a cyclic barrier does. Then we're going to create something called a countdown latch, which is used by the main thread to wait for all the other threads to finish. So it's an exit barrier. This here is an entry barrier, and this is an exit barrier. And then once we've initialized those things, we're going to go ahead and create runnables, which are tasks, and we're going to go ahead and execute them by giving them to the thread pool executor, which will schedule them and run them when there's room for a thread to do some processing on the being. So that's essentially how we do concurrency with Java 5 level abstractions, like the executor framework. This particular abstraction, very feature-rich, very optimized, very clever, but it's also, honestly, a bit tedious and error-prone to program, and doesn't scale well for modern multi-core processors. So as you start getting lots and lots more cores, which we have today, this model doesn't really scale up very well, even though it's better than the alternative that was Java 1. So what did that do? That motivated a whole bunch of other modern Java concurrency and parallel mechanisms, like parallel streams and completable futures, which came out in Java 8, and then reactive streams, which is something that came out in Java 9 and beyond. These are all things we're going to talk about next time, because that's parallel processing, and that's the evolution of where things went in that time frame. So that's kind of the end of the brief overview of concurrency support. The key things I want you to come away with from this is Java's had concurrency support since the beginning. They added some things to it over time, about 20 years ago, but there were deficiencies, and as we got smarter about how to write more scalable programs to take advantage of the hardware advances, they added support for parallelism, which will be the next thing we're going to talk about.